Hi everyone, thanks for watching my YouTube contents. I'm Sangwoo. In this video, I would like to share how to get survivor probability from survivor analysis in Excel and R. I prepare simple data from R library. The name of dataset is ovarian. As you can see, there's simple explanation about each column. So let's assume that we are interested in survivor probability by using FEO time, survivor censoring time, and FEO stat, censoring status, and RX treatment group. Then in our program, we can do this survivor analysis by using serve fits function with serve format like this, FEO time, FEO stat. Then from summary function, we can see survivor probability for RX group by each RX group. So this is first RX group and second RX group. Of course, it provides standard error and confidence interval. Right. Right. Let me show you how to get this survivor probability and standard error and confidence interval in Excel. Right. I will show you how to get survivor probability for first group. Then you can apply the formula for the second group. Right. Let's get number of risks. Number of risks can be calculated by using count function. And you need to fix the last cell here. Then you can apply this formula for other cells. And number of event is same as FEO stat. So by probability can be calculated by 1 minus G2 over H2. H2 over G2. And the first probability, survivor probability is same as probability for shortest time, right? Then second survivor probability can be calculated by first survivor probability multiplied by second probability. And we can apply this formula for other cells, right? Then let's move on this part. In order to calculate standard error, we need to understand this part. So let me show you how to get this part first. So D number of events over N number of risks times number of risks minus and number of event then standard error can be calculated by survivor probability times square root of sum of this formula. So again, this one, this one. We need to fix this one till 2. Let's fix the first cell here. Okay. Then we can apply this formula for other cells. This is same as this one. So again, it's a little bit complicated to understand the standard error, but as you can see, this part, sum of this part can be calculated by using this function. So you need to fix the first cell, right? This part. Then you can get standard error. Then let's get confidence interval. So we can use this formula. Survivor probability times exponential of minus norm dot s dot dist. Let's set alpha as 5%, then 1 minus alpha over 2 is equal to 0.975. Okay, and then let's then multiply by square root of this part, standard error, and these parts. Sorry, sum of but you need to fix this one. Sorry, we need to use norm.s dot imv, and we can apply this formula for other cells. Oh, sorry. Then this is same as this one. Okay. Right. Okay. Then upper confidence interval. Let's get same formula for the only difference is minus sign here, so let's delete this one. Okay, and as you can see, it's over value 1, so we can add additional condition. So if this formula, the value of this formula is greater than 1, then let's change it as 1, and if not, let's keep the formula. Ctrl C and apply this formula for other cells. Right, then you can get same output here, right? So again, this part, FU-stat, these two rows shows FU-stat as 0, so that's why it doesn't show, our output doesn't show these two different time values in the output. It only shows event probability, event survival probability, right? I hope it was useful to understand how to calculate survival probability and standard error and confidence interval from server-fit function. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sangwoo Kim. In the previous video, I showed you how to do survival analysis in XLNR. In this video, I would like to show you how to draw Kaplan-Meier plot, which is one of the famous plots to understand survival probability. And it is very useful to compare survival probability among each group. In Wikipedia, there is Kaplan-Meier estimation information. So in this video, I would like to show you how to get this kind of Kaplan-Meier plot in XLNR. Let me use the same data, which is this one, ovarian data. And in our program, if you use plot function and legend function, you can draw this kind of Kaplan-Meier plot. So I would like to show you how to draw this Kaplan-Meier plot in Excel. right? We need to use this survivor probability by FU time. So let's get FU time data and survivor. Right. So as I explained, this time value doesn't have any event, so it doesn't calculate survivor probability in R, but it's actually same as previous probability. So, I mean survivor probability. So in order to draw a Kaplan-Meier plot in Excel, we need to rearrange this data. Let's use ID variable. Okay, and let's add small value. And let's get same value here, same survivor probability. Then let's make a value, copy and paste the value here, rearrange data by ID value. Then let's add two more row. So as you can see, there is a line here between 0 to 200. So let's get an FU time as 0 and survivor probability is 1. Okay. Then let's change the second, every second data. So minus 1, and let's apply this formula for other cells. Okay. Let's leave it there here. I will show you how to fill this data later. Okay. And this one. Again, change it as RX1. Let's change it as RX2. Survivor probability. So in the previous video, I showed you how to calculate survivor probability for group 1. This formula is actually the logic same as this one. Again, for the rest of time data, let's apply same probability, survivor probability. Let's select this one, and then let's change the order. Sorry, let's make a value and let's change order. Okay. Then again, we need to put a value by using this formula. And the last one again. So let's the largest value for group RX1 is around 1100, and for group 2 1200. So let's to make it same, let's say 1300. Okay. Then let's put same value here. For every time as 0, we can put allocate survival probability as 1, right? Then let's draw a plot for Rx1 and Rx2 each. So inserts and scatter plot, and this one. This is for group 1, Rx1. For this one. Okay. So this is for Rx1 and Rx2. In order to overlap this one, let me just copy and paste here. Again, okay, sorry. Then let's copy this Rx2 graph and Ctrl C and click this graph and Ctrl V. Then it automatically overlaps two graphs here. Sorry, we need to add label. So let's add regions, and then Ctrl C and Ctrl V. Then it shows two regions here. Okay, let's compare this one and this one. Again, as you can see, if you change line color and style, then it's same as, so actually let's say this one it should be blue, and this should be red. Sorry. And you can change format as a dotted line. So as you can see, okay, right, so it's same as our output. Cool. So again, you don't need to actually understand complicated way to draw a Kaplan-Meier plot if you are familiar with our program. But I just wanted to show you how to draw a Kaplan-Meier plot in Excel by using this actually in this way. So I hope it was useful to understand how to draw Kaplan-Meier plot in Excel. Please click like and subscribe if it was useful or fun for you. Thank you. Hi everyone, thanks for watching my YouTube content. I'm Sangwoo Kim. Today I would like to show you how to do row rank test in Excel and R. According to Wikipedia, the row rank test is a hypothesis test to compare the survivor distributions of two samples. There is one reference site I have used for this video. It shows a very structured explanation to understand row rank test. These are main contents to clearly understand row rank tests. As you can see, we need to generate this continuous table to get observed to fail and also others. And it shows also expected value and variance, and also related statistic. We also can get z or square of z, which is actually chi-square. Then we can do statistical test whether two samples are significantly different or not in terms of survival probability. In our program, you can use serve-diff function from survival library. Then you can do log rank tests. It shows chi-square statistic and p-value. So under 5% significance level, the p-value is greater than significance level. So we can say that we cannot reject null hypothesis. It means that we accept null hypothesis, and also we can interpret it as there's no significant difference in terms of survival probability between two groups. Let me show you how to get this related data statistic in Excel. I have prepared data which was used to show you to help you understand Kaplan-Meier plot. And as you can see, there's a time variable, and this is related to event, and there are two groups, group information, right? In log rank test analysis, we only need to consider event data. So I just highlighted it as green. So let's copy and paste here. Right. Then, as you can see, we need to consider this 2x2 continuous table. And I hope you are familiar with chi-square test statistic. But as you can see in this model, they are all related to time factor. So it says at least at tau z, which means it depends on time data. So it's easy to calculate observed value because there's no greater than 1. So only it has got one events as one value. So observed value is 1. And for purple color, event value is 0. Sorry. Then for second group, the observed value is actually 0 because these yellow cells are related to group 1. And for this event time, it actually should be 1 because all data are actually 1 as an event. Then not observed, in order to calculate not observed value, so we need to think of this formula, count if, range from group 1, fixed color, and comma, greater than event time. Then we can apply this formula into other cells. And for group 2, same formula, count if, range from group 2, comma, greater than event time. Right, and marginal sum for first row, sum of observed value and not observed value. And marginal sum for second group can be calculated by like this formula. And total samples actually can be calculated by first marginal sum for first row and marginal sum for second row. And expected value for group 1, this one, we can use this formula. Okay, marginal sum for first row times observed value from group 1 plus observed value from group 2. and divide by total samples here. Right. So we were able to calculate expected value for group 1. Actually, marginal probability for this one should be 1. So expected value for second group is actually 1 minus expected value of group 1. Right? Or you can directly compute expected value for group 2 by using same logic. Observed value for second group times marginal sum from group 2 and over total samples. Sum observed value plus this one and total. There are two ways you can calculate expected value for group 2 once you calculate expected value for group 1, right? And VJ has got this formula, so it means that there are 4 components, numerator part for numerator part, and denominator part actually use total sample size, and this one is actually marginal sum of first row, second row from row point of view, and first component and second marginal sum for column point of view. So let's get observed value. Let's get this one first. Should be this one, and times this one, and times dj. Actually, observed value from group 1 plus observed value from group 2, and times the last term, this part, it should be this one, marginal sum, this one, sorry, 12 plus 13, and divide by this one, square it, times total sample minus 1, and in order to calculate this part, let's first calculate observation. Observed value minus expected value. So observed value minus expected value. Okay. Right, then expected value for group 1 is the sum of this one, and expected value for group 2 is from column N, and observed value for group 1, sum of column F for group 2, right, and let's calculate this part. Observed value minus expected value and square it over expected value. We can apply this formula for group 2. Right, then this one, observed value minus expected value squared and over and sum of Vj variance, this one, and this part is same, actual value minus expected value squared over sum of V. Then chi-square value as actually let's use this part. So sum of squares over sum of V, right? This one is same as this one, right? Then p value is 1 minus isq dot dist, chi-square statistic, degrees of freedom as 1, true. Right. So this p value is same as this one. Again, under 5% significance level, the p value is actually greater than significance level. So it means that we cannot reject null hypothesis. It means that there's no significant difference between difference about survival probability between two groups. I hope it was useful to understand how to do log rank test in XLNR. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sangwoo Kim. Today I would like to show you how to estimate parameters for Cox proportional hazard model in survivor analysis. Basics of Cox proportional hazard model is like this. So HT, hazard function determined by set of P covariates, and it can be calculated by baseline hazards multiplied by exponential of regression coefficients. I mean this covariates part. So this part, the quantities exponential of beta I are called hazard ratio, this one. The value of beta I from regression analysis greater than 0 or equivalently a hazard ratio greater than 1 indicates that as the value of ith covariate increases, the event hazard increases, and thus the length of survivor decreases. I will explain the meaning of this text a little bit later. There are some key points we need to understand related to Cox proportional hazard. So once you divide by lambda t given x, actually we can get exponential of beta covariates. The right hand side is constant over time, as you can see. No term has a t in it, and the relationship is actually called proportional relationship. And also there is no intercept term in the model. The Cox model ranks 1 because the baseline has lambda 0t takes the place of it, right? And in order to estimate parameters for Cox proportional hazard model, we actually need to use log partial likelihood. The formula for log partial likelihood is like this. This is a little bit different from typical log likelihood because of this part and this part. Right. In our program, you can do Cox proportional hazard analysis by using Cox pH function from survivor library. Right. So once you get this output, now you can understand how to interpret exponential of coefficients. Again, when you see exponential of beta I, this is actually a hazard ratio, right? The coefficient, exponential coefficient for Rx is below than 1. It means that actually the event hazard decreases, right? However, in terms of age covariate, the exponential of coefficient is greater than 1, right? It means that the length of survivor decreases. So it means when age is increasing, the length of survivor is decreasing. All right. Let me show you how to get these coefficients in Excel by using this log partial likelihood formula. Right? We actually set theta j as exponential of xj multiplied by beta. So let's set beta as 0, it's the initial value. Then x beta can be calculated by and merge of data matrix, comma, and coefficients. Then press Ctrl Shift Enter. Right. We can apply this formula for other cells. And exponential beta, actually this one, theta j, can be calculated by exponential of x beta. Right. Then we need to clearly understand this part and this part. It means that we only use this summation once event happens. And this is the sum of all occurred events. So if your stat equals 1, then we use the formula. So x beta is 1 minus log of sum of theta j. So sum of theta j. Then we need to fix the last column here. And if v2 is not equal to 1, then we give it value as 0. Right. Then let's calculate sum of all partial likelihood, this part. Right. So this sum of partial log likelihood, actually this one. So once you have a Cox page model, you can calculate basic, log likelihood for initial value, right? And it provides two log likelihood. So the first log likelihood is from initial value. Then let's minimize some of log likelihood to get regression coefficients for Cox pH model. Click solver. Then we can set objective, this one, and we want to maximize this log likelihood, sum of log likelihood, while changing this regression to these two coefficients. Then click solve. Right. Then this is same as this one, right? So exponential of coefficients. Cool. So again, I showed you how to estimate parameters by using log partial likelihood in this video. So I hope it was useful to understand how to apply this formula to get regression. These coefficients for Cox proportional hazard regression model. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube content. I'm Sang Kim. Today, I would like to show you how to calculate concordance from Cox proportional hazard model in XLNR. There is one reference site I use for this video. The concordance statistic is most used measure of goodness of fit in survivor models. And in general, we use observed data and predicted data values, right? And these predicted data values come from the linear predictor from a fitted model. And concordance is defined by this formula. So the main meaning of this formula, actually x and y has got same direction. In our program, if you specify type as LP in predictive function, then you can get this linear predictor. And by using, if you use concordance function, then you can get concordance statistic. And concordant and discordant, and actually in this data, there's no tied data. So I would like to show you how to get this concordance statistic in Excel. I hope you already know how to calculate, how to estimate these coefficients from previous video, right? So let's get a linear predictor here. Rx minus average of Rx variable and multiply by estimated coefficients plus age minus average of age variable and multiply by estimated coefficients. Alright, as you can see, we were able to get same linear predictor. Then let's see the relationship between FEO time and linear predictor. Right. As you can see, it shows actually negative relationship. So let's make it as a positive relationship here. Times -1. Right. Then concordant. We can use count if as function. If you use count if as function, you can specify more than 2 conditions. So criteria from FEO time and fix last cell and condition greater than first value. And let's specify second condition. Again, fix last cell. This one. Right, then we can use this formula for discordant. Again, so main concept of this concordant is to have same direction. So discordance, if you change this symbol as less than, then it means discordant. Right. Then let's get concordance here. So we only consider event. So sum if range from FEO stat and comma events actually coded as 1, so 1, comma, and some range from concordant. Right. And discordant range from FEO stat, comma 1, comma, and discordant. Alright, then concordance statistic. Right. So we were able to get concordance statistic by using concordant and discordant. Right. So actually I wanted to cover how to calculate standard error for concordant statistic, but there's no actually concrete contents to fully understand standard error for me. So if I have chance, I mean, if I will study more about how to calculate standard error in the future. So once I clearly understand it, I will try to make it video, right? Anyway, I hope it was useful to understand how to calculate concordance statistic in XLNR from this video. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sangwoo Kim. Today I would like to show you how to calculate the baseline hazard for cockpit model in XLNR. If you study survivor analysis, I think you are very familiar with this notation. So an estimate of baseline hazard function is given by this formula. With Vita 0, this reduces to Nelson-Altshuler-Allen estimator. The baseline survival function is given by this formula, and this may be obtained by estimating capital H0t as a cumulative sum of the estimated hazard small h0tj for tj greater than fixed t, right? And with all covariate values set to 0, then we can calculate baseline hazard. In many websites, there are many questions and answers to clearly understand baseline hazard. And in our program, actually, you can calculate baseline hazard from base has function, but you need to be careful about using center option. Actually, base has provides cumulative baseline hazard. To get an estimate of cumulative hazard function, typically the Breslow estimator is used. Right, let me show you how to calculate baseline hazard in two different ways, right? So again, I set coefficients as 0, right? Then let's get cumulative baseline hazard like this in this column. So let's calculate x beta from emerged and specify covariate variables and comma and coefficients, and press Ctrl Shift Enter. Then exponential of x beta can be calculated by exp function, and log likelihood for each observation can be calculated by if event occurs, then x beta minus log of sum of exponentiated beta and comma 0. Right, then exponential of log likelihood for each observation. Okay. Right. So this one, so we can use this exponential of log likelihood to calculate cumulative baseline hazard. The first observation is same, and second observation is sum of this one. Then this is actually same as our output, right? And second option, second way to calculate cumulative baseline hazard is to use Breslow estimator. This is the formula, and as you can see, so this part, when you specify beta as 0, then it becomes exponentiated 1. Then it means that we only need to consider count number of events, right? J belongs to Ri. This is actually event cases. So baseline hazard can be calculated by B2 minus count of, this is all possible outcomes events, right? Right. Sorry. Okay, this is same as exponentiated of log likelihood. So again, cumulative baseline hazard, when you specify, when you consider zero covariate. Right. Okay, this is same as our output. Right, but also if you when you consider covariate Rx or two covariates, right? So we can also calculate baseline hazard with center option. So I was struggling to calculate this baseline hazard for a long time, but just I got some clues from this reference site. So let me show you. Right. So again, in R, the base has function will compute cumulative baseline hazard function, and be sure to use the option centered F to cause it to estimate cumulative hazard at beta equals 0. The default is to estimate it at the mean of the covariates. This will often not make sense, particularly for categorical covariates such as treatment indicators, X, or race. So I will show you when we consider two covariates how to calculate baseline hazard, right? Right. So in the previous video, actually I showed you how to calculate X beta and log likelihood for each observation, and we can calculate estimate. We can get these estimate coefficients from solver data and solver. So set objective. This should be sum of log likelihood, and we need to find optimal estimate coefficient by changing variable cells this year. This one. Oops. Okay. Oops, sorry. Click the wrong one. Super. It should be max, right? All right. So this is estimated coefficient. So let's get baseline hazard and cumulative hazard when centered false or true. So this baseline hazards can be calculated by if B2 equals 1, which means event, then 1 over sum of exponential x beta Alright, as you can see, so this baseline hazard is same as this one when centered option is false, right? This is sorry, this is cumulative. This is like hazard. So baseline hazard. So let's get cumulative baseline hazard. So again, this one can be calculated by this one and previous one plus this one. Right, this one is same as this one. Right, so it means that when you specify center as F first, then this is from actually exponential of log likelihood, right? So we were able to calculate baseline hazard, and finally we were able to calculate cumulative baseline hazard. Again, if you specify center as true, then actually as it says, the default is to estimate at the mean of the covariates, right? So we can calculate baseline hazard with the centered option as true. So cumulative baseline hazard multiplied by exponential of this part. So average of Rx times estimated coefficient plus average of age covariate multiplied by estimated coefficient. So this is same as this one. Right. So again, when you specify center option as true, then we consider mean of covariates, right? This part. That's why it in this, as I mentioned, where is it? Okay. As you can see, yeah. Baseline hazard with center option as true, we consider average of or covariate. So if any variable is categorical variable, sex or race, like this, then that's why it says we need to be careful, right? Right. So, but the main purpose of this video to show you how to calculate baseline hazard and cumulative baseline hazard function in Excel and R. Typically, we are less interested in baseline hazard, but I hope this video is useful to clearly understand how to use baseline, how to calculate baseline hazard. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sangwoo Kim. Today I would like to show you how to get predicted values for Cox pH model in Excel and R. There's one reference site I've used to explain predicted values. So in our program, actually, it provides 5 different predicted values from this function, right? So it's based on sorted data by FU time, then you can get these predicted values. As you can see, when you specify type as LP, then it means linear predictor, and if type as risk, then it means exponential or beta. And also, it provides explanation about how to read predicted value related to risk. So again, a risk score above 1 is higher risk than the average of in the population, and below 1 is a lower risk than the average in the population. If you specify type as expected, the expected number of events for an individual over the time interval that they were observed to be at risk. And if you specify type as terms, it means the individual components of the linear predictor eta is returned. And unfortunately, this website doesn't provide survival probability. So there's one on our site, Stack Exchange, and it provides the explanation about linear predictor, risk quantity, and expected quantity. And as you can see, this expected quantity does require an estimate of a baseline hazard. I will show you, in the previous video actually, I showed you how to calculate baseline hazard. But in this video, I will show you again. And lastly, it also explains that the survival probability can be expressed as exponential of negative expected quantity, right? So this is our output for first 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 records. This one, and it provides LP, risk, expected survivor, and RX and age. So let me show you how to get these predicted values in Excel. So LP is, as you can see, this formula, but actually in our program, actually X transpose X must be centered. So let's get RX minus average of Rx variable times Rx veta, veta hat plus age minus average of age variable times age coefficient, right? Control C and Control V. So it's same as our output, as you can see. And risk can be calculated by exponential of linear predictor. So exp of J2, right? So this same as our output again, right? The next one is actually expected value. So in order to get expected value, we need to understand and calculate cumulative baseline hazard and with centered true option. So firstly, let's get baseline hazard. So if FU_stat equals 1, then 1 over sum of exponential beta x beta and fix last cell. And if FU_stat is not equal to 1, then let's give a value as 0. Then cumulative baseline hazard, first one should be the same as this one, and the next one is previous baseline hazard plus current baseline hazard. Okay, and cumulative baseline hazard, sorry, this one should be hazard. All right. Hazard with center option as true, then cumulative baseline hazard times exponential of average of Rx variable times coefficient plus average of age variable, fix them all, and times age coefficient okay, so it should be same as, let me see, should be this one. So anything wrong? This one, we want to calculate expected value from cumulative baseline hazard. So expected value can be calculated by cumulative baseline hazard times risk. Okay, so again, expected quantity can be calculated by baseline hazard times risk quantity. Okay. Same as our output, I think so. And one thing you need to be careful in terms of expected value, it can be over the value 1, right? So again, the expected value can be higher than value 1, right? And survival probability, this one, exponential of negative expected value. Okay. same as our output. Yes, I think so. And the last one, Rx value minus average of Rx variable and times coefficient and Tom's value for age variable, age minus average of age variable times and coefficients. Right? Same as our output. So in summary, in this video, I wanted to share how to calculate a linear predictor, risk, and expected, survivor, and terms. So actually, these are from predict function in our program, as you can see, this one. And also, I hope you understand how to use type different type in terms of predicted values, right? Again, so one thing you need to be careful about expected value is that actually this value can be more than value 1, right? This is a survival probability, right? Right, that's it for today. I hope it was useful for you to understand how to predict, how to get predicted values for Cox pH model in Excel and R. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sang Kim. Today I would like to show you how to calculate standard errors of coefficients for Cox proportional hazard analysis in Excel and R. In the previous video, I showed you how to get these coefficients by using partial log likelihood. And in our program, actually, we can calculate this one, coefficients by using Cox pH function. And I haven't explained how to calculate standard errors and p-values in the previous video. So in this video, I would like to show you how to calculate these standard errors and p-values. There is one good reference site I have used for this video. So we need to clearly understand how to calculate Hessian metrics to calculate standard errors for Cox proportional hazard analysis. And we can derive beta hat from this formula, okay, by using Newton-Raphson method. So again, if you use Cox pH function, you can simply and easily calculate get coefficients and standard errors. But if you use this algorithm, actually you can manually calculate coefficients, and also by using this form, you can also calculate standard errors in Excel, right? All right, let's focus on this main algorithm part. So we need to calculate eta, hazard risk, P, and W metrics to calculate, to get standard errors in Excel. So we are going to use many matrix computations in this video. So let's give a name for simple computation. For this part, let's give a name as X. Okay. And this is hazard. Hazard actually comes from column G, exponential of G2. And risk is actually sum of hazard. You need to fix the last cell like this. Then let's get P matrix. So this is hazard and risk from this one, right? Let's in order to get P matrix, in our program, you need to use auto function. So this is same as if we look up value from column E, comma, table array over, if we look up value from column F, and table array from this one, third column. Okay. Then we also need to give a value as 0 for upper triangle part. So if greater than this one, yeah, let's give value 0. If not, let's use this formula. Okay, let's give a name as P, capital P, and diagonal of events. So if row same as column, then let's get, if we use the value here. If not, let's give a value 0. Right. This is diagonal matrix, and let's give a name as D. Let's get W matrix minus P, and merge minus P, comma D, and again merge, comma transpose P. Okay, and press Ctrl Shift Enter. Okay, and let's give a name as W, capital W. And then the algorithm actually replaces original diagonal elements with new diagonal elements by using this formula. Okay, so merge P, comma, and the matrix again, and merge, comma, transpose minus P, and press Ctrl Shift Enter. Okay, let's give an okay, and then let's generate new W matrix. So again, if row is same as column, it means diagonal elements. Let's get diagonal W, diagonal elements from this one, and if not, let's get the value from W matrix. Oops. Sorry, we need to fix column here. Okay. Right. Then let's calculate this one, coefficients, by using this formula. And merge. Sorry, we are going to use this W from updated W matrix. So Let's delete name W. Let's give a name for this one, this W matrix, SW. Okay. Merge transpose X, W, and merge comma X, and solve means inverse, so M inverse, and merge comma transpose X. Sorry, we need to calculate this part, so and merge P comma D column here, and press Ctrl Shift Enter. This one, FU step minus column K. Merge transpose X comma W, and merge comma X. And then as you solve means inverse, so M inverse, and transpose of X, and merge comma transpose X, and merge comma and plus, then press Ctrl Shift Enter. Right, so this is same as this one. Hessian matrix, merge transpose X comma W, and merge comma X. Okay, then covariance matrix is actually inverse of Hessian matrix. Okay, then standard error coefficient for Rx is equal to square root of first diagonal elements and square root of second diagonal elements. Okay, so this is same as R output, and Z value can be calculated by coefficients over standard error. P value in our program actually use two-side P values, so this can be calculated by 1 over absolute value of Z, comma mean as 0, standard error as 1, and cumulative. And times 2. Let's see what's wrong. Okay, then 1 minus, then 2 times. Right, this is same as our output. So Uh, as you know, under like a 5% significance level, Rx is not significant for Cox at this model, and age is significant variable under 5% significance level. Right. So if you clearly understand this algorithm, I think you, you will be able to calculate coefficients and standard errors in Excel. I hope it was useful to understand how to calculate standard errors and p-values for Cox proportional hazard model in Excel. Again, you need to also understand Hessian matrix, and actually covariance matrix comes from Hessian matrix. Then you can calculate the standard error for Cox proportional hazard analysis. I hope it was useful to understand how to calculate standard errors and p-values for Cox proportional hazard model in XLNR. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sangwoo Kim. Today I would like to show you how to do goodness of fit tests for Cox proportional hazard analysis in XLNR. In the previous video, I showed you how to calculate covariance matrix in XLNR. I think this covariance matrix is crucial part to clearly understand how to do goodness of fit test in XLNR. Right? So please refer to that previous video if you want to know more about how to calculate covariance matrix. But in this video, I would like to focus on how to do goodness of fit test in XLNR. In our program, once you have proportional hazard model, which is named as CPH1, then when you use summary function, then you can get these coefficients, and also at the bottom of the result, you can see three goodness of fit test results, right? So this is how to interpret the results. Under 5% significance level, these are all significant. So it means that at least one independent variable is significant for proportional hazard model. The great part, actually, I showed you how to calculate these three statistics manually in our program, right? So likely ratio test can be calculated from log likelihood from null hypothesis, null model, and final actual model. World test, as you can see, this is the matrix computation, and the middle part, actually, you need to calculate information matrix. Information matrix is actually from covariance matrix from Cox proportional hazard model, and you need to use inverse of information matrix. And in terms of score test, you need to calculate detailed score from this model, right? So again, in order to calculate score statistic, you need to use actually a variance matrix from fit zero, this one, right? So I would like to show you how to calculate these three statistics in Excel. Right. Again, in the previous video, as I mentioned, I explained how to calculate covariance matrix from Hessian matrix. So let's skip it for this video. Anyway, let's get covariance matrix from this one. Control C and Control V. And also we need to use covariance matrix from reduced model to calculate the score test. So let's get covariance matrix from reduced model. So you need to set coefficients as 0. Then you can get this covariance matrix. Control C, Control V. Right. And also first part, this one, I would like to show you how to calculate likelihood ratio test. So In this test, we need two different sum of log likelihood. So these are from null hypothesis. Okay. Let's get coefficients from by using solver. Okay. And this is sum of log likelihood from this model. Right. Then likelihood ratio test 2 times null hypothesis minus find our model hypothesis model likelihood ratio. It's better to use 2 times full model, full model minus null model. Okay. Then degrees of freedom is 2 because there are two independent variables, and p-values can be calculated by 1 minus chi-square distribution degrees of freedom, true. Okay, this one. Okay. Then let's get wild test statistic. This one. It can be calculated by using this formula. So invert and transpose of regression coefficients, this one, and inverse of covariance matrix, and invert comma and coefficients, and press Ctrl Shift Enter. Then degrees of freedom 2, and we can apply same p-value formula for wild test result. Okay, and score test can be calculated by using score vector. This score vector can be calculated from this one. So let me use this formula. Okay, so I want to show you how to calculate these parts in here. So a underscore ik can be for rx variable can be calculated by sum of rx fixed final cell and count for rx variable fix the final cell, last cell, and Ctrl C and Ctrl V. Then aik for age variable, sum of and count of age variable, and fix the last cell. Then score for Rx, this one should be used for Rx minus aik for Rx variable, and score for age can be calculated by age variable minus aik for age variable. Okay. Ctrl C and Ctrl V. Right. Then we need to consider event case. So sum if, range from column B, and criteria as 1, and some range from column L. Okay, and for age, some if range from column B, comma 1 as criteria, and some range from column M. Then score test can be calculated by invert or transpose X variable, this one, and comma, and covariance matrix from reduced model, this one, and invert, comma, coefficients, and press Ctrl Shift Enter. Sorry, it should be sorry, let's calculate again. Invert transpose of score vector. Sorry, I used these coefficients, but we need to use score vector, this one, comma, covariance matrix from reduced model, and invert, comma, score vector. Then press Ctrl Shift Enter. Right, which is same as our output, and degrees of freedom is 2, and p-value we can use same formula, okay, which is same as our output. Alright, that's it for today. So in summary, in order to calculate standard errors, in order to calculate goodness fit test statistic, we need to understand how to calculate covariance matrix and covariance matrix from reduced model, right? Then we can calculate the wild test and score test statistic. Actually, likelihood ratio test statistic can be calculated from two sum of log likelihood from null model and full model, this one. Then we can calculate p-value. So it means that actually this is goodness of fit test. So under 5% significance level, we can say that this at least one independent variables are significant. So it helps to increase goodness of fit test. Goodness of fit of Cox proportional hazard model. I hope it was useful to understand how to calculate the three goodness of fit test statistic, and also how to interpret it. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sangwoo Kim. In this video, I'm going to show you how to get Breslow estimation with ties for Cox proportional hazard analysis in Excel and R. In the previous video, I showed you how to get Cox pH coefficients by using ovariant data. And for this video, I actually added 3 more samples and colored it by green. There's one reference site I have used for this video. So when you have tied events like this, Cox pH fit approximates the partial likelihood of the model by either Breslow's method or Ephron's method. The simplest approximation method is Breslow's method. This method uses the same denominator for each tied set. In our program, if you specify ties option in Cox pH function, then you can get Breslow coefficients for Rx and H. Actually, Cox pH use Breslow option as default. Right, let me show you how to get Breslow coefficients in Excel. So again, for example, assume that the first two events are tied, that is T1 equals T2, and ascending order from T2 to Tn. In Breslow method, the denominators of the first two terms are the same. Please mind this formula. Then let's firstly get Cox pH coefficients in Excel. So emerge comma and coefficients, and press Ctrl Shift Enter. And exponential of x beta can be calculated by using exponential function. And log likelihood for each observation. If fu stat equals 1, then x beta minus log of sum of exponential x beta. Then you need to fix the last cell. Okay. Then if v2 equals is not equal to 1, let's give a value as 0. Control C and Control V. Then again, sum of low likelihoods. Okay. Then we want to actually maximize this sum of low likelihood by changing this one. Okay. And uncheck this option and click solve. Right. So this is actually Cox pH coefficients, right? We haven't considered this tide option in log likelihood. Again, please remember that the denominator must be same. So let's change the log likelihood for tide samples. So again, we need to use same denominator. So it has got another same data for FU time. So let's change this to F4, this one. Okay, and for this one, because this observation actually has same FU time, so we also need to change it. Okay. This one. Right? Then let's find again coefficients by maximizing this one. Server, and let's click it again. Okay, as you can see, it has been changed, and it's very similar to this one. Our output. I guess the small difference actually comes from different optimization algorithm, right? In our program, we actually use Newton-Raphson algorithm, but in Excel, it actually uses this GRG nonlinear algorithm, right? But the main thing what I wanted to say in this video is to help you understand how to get log likelihood when there are tides data. I hope it was useful to understand how to get breath flow estimation for Cox proportional hazard analysis with tides. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sangwoo Kim. In this video, I'm going to show you how to calculate Nelson-Aaron estimator for Cox proportional hazard analysis in XLNR. According to Wikipedia, Nelson-Aaron estimator is a non-parametric estimator of the cumulative hazard rate function in the case of sensor data or incomplete data. And it is used in survival theory, reliability engineering, and life insurance to estimate the cumulative number of expected events. An event can be the failure of a non-repairable component, the death of a human being, or any occurrence for which the experimental unit remains in the failed state, from the point at which it changed on. The estimator is given by this formula. In our program, there are specific functions to calculate Nelson-Aaron estimator, which is Nelson-Aaron function in mice library. So it calculates the cumulative hazard rates which is same as Nelson-Aron, which is named as Nelson-Aron estimator, and this is how to use this function in R. In our program, actually, I have found two ways to calculate the Nelson-Aron estimator. The first one is by using mice library. So once you activate mice library, you can use Nelson-Aron function, specify data and time variable and status variable. And also, you can get Nelson-Aron estimator from survivor library, as you can see. Once you specify serve formula with tilde 1, then you can calculate Nelson-Aron estimator from predict option, predict function, and you need to specify type as expected. Then, as you can see, from mice fit and cox fit, you can calculate Nelson-Aron estimator. Right. Let me show you how to get this Nelson-Aron estimator in Excel. So firstly, you need to calculate number of observations at disk. So count. Fix the last cell. Right, this is a number of observations at risk, and hazards can be calculated by if you set over number of observations at risk. Then cumulative hazards. The first one is same as hazard, and the second cumulative hazard is sum of first one and second hazard. Then you can apply this formula for other cells. Right. So this formula explains how to calculate cumulative hazard, and in Excel you can simply calculate cumulative hazard by using this formula. So this is how to calculate Nelson-Aron estimator in Excel and in our program. I hope it was useful to understand how to calculate Nelson-Aron estimator in Excel and R. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sangwoo Kim. In this video, I would like to help you understand about exponential distribution before covering parametric survivor analysis. The characteristics of exponential distribution is like this. The exponential distribution is used to model data with a constant failure rate. And the higher the hazard, the smaller the expected survival time. And exponential distribution is a specific distribution from Wyville distribution. So let's say the cumulative distribution for Wyville is like it has this formula, and when beta equals 1 and gamma equals 0, then it has standard exponential distribution. So this is typical expression about cumulative exponential distribution. So let's say we can pronounce the eta or eta. This is a scale parameter. So typically we use 1 over eta equals lambda. And in Excel, we can use expon.dist function. And we can specify time variable and lambda. And for cumulative density function, specify true option. And this is exponential CDF, as you can see. When eta is smaller, then it has steeper curvature like this. And if you consider derivative form of cumulative density function, then you can get PDF. The PDF form of exponential distribution is like this. So as you can see, Again, eta is a scale parameter. In Excel, you can use expon.dis function with false option. Then it shows different PDF by different eta. So smaller eta has got a very steeper curve like this compared to other eta value. And as I mentioned, I'm going to use exponential distribution for survivor analysis in the coming YouTube contents. So let's think about how to use exponential distribution for hazard function. So this cumulative function, this is a cumulative function for exponential distribution, and 1 minus ft is actually survivor time in survivor analysis, and it can be written as like this form, right? And hazard of t equals ft over survivor time, and if you divide by this one by st, this one, then you can get 1 over eta. So again, I mentioned that 1 over eta equals lambda. So lambda is actually hazard function. And if you consider cumulative hazard, then you can you can use integral from 0 to time t, 1 over eta. So you can get 1 over eta is actually constant. So if you use integral from 0 to t, actually it has 1. So it means the value of this one is actually 1. Sorry, t. So t times 1 over eta is actually cumulative hazard function. And typically we use actually likelihood function to estimate lambda. So this is formula for likelihood function again. So we consider likelihood for each time. Then if you multiply by all different time, then you can get this formula. All right. Again, and typically we also use log likelihood function. So if you take a logarithm of likelihood function, then you can get this one. And also, if you study statistical inference, then you will learn how to actually is same as 1 over average, 1 over mean. So lambda is actually equal to n over sum of ti, right? So, all right. So let me show you how to get how to estimate lambda of exponential distribution in Excel. Again, so in PowerPoint, I showed you how to get this cumulative distribution. So again, if you use expon.dist function, then you can get CDF for exponential distribution. And if you specify false option in expon.dist function, you can get a PDF of exponential distribution. And I showed you how to get how PDF is different based on different eta value. So let me use again ovarian data. All right. So in this video, let's only focus on time data. In this video, I'm not going to consider stat or independent variables, right? Again, as I mentioned, lambda can be calculated by count of time and over sum of time, right? Then let's get average of time. All right. Again, if you take 1 over lambda, then it actually takes same value of average of time. Okay. So I hope you clearly understand the relationship between lambda and average of time. And again, next, let's get lambda from log likelihood function. So log likelihood can be calculated by using this formula. So count of time variable times log of this one lambda, this value, negative lambda times sum of every time. Right. So let's initially set lambda from considering this lambda. So let's say 0.05, something like that. Right. So we want to find optimal lambda to maximize this log likelihood. Right. Then go to data and click solver. Okay. We want to maximize this log likelihood by changing this lambda value, right? And uncheck this box and click solve. Okay, I think it should be more similar to this one because it actually doesn't converge if you initially set if you do not set lambda, initial value lambda as close to actual lambda, I think, but it's okay in our program. So let's click again. Okay. So if you use our program, the Newton-Raphson algorithm is appropriate to find this lambda, but in Excel, actually, the only option we can use to find lambda is actually solver. Solver use actually GRG nonlinear method. Okay. So again, by using solver, I found optimal lambda, which is same as this one. Okay. Right. This is how to find optimal lambda for time data. Right. So I hope it was useful for you to understand how to use exponential distribution to find optimal lambda in Excel. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sangwoo Kim. In the previous video, I showed you how to get the optimal lambda of exponential distribution by using Excel. So the most important thing to get optimal lambda was to understand log likelihood function, right? Then we were able to get optimal lambda by using this log likelihood function or this formula and over sum of ti. So in our program, actually, there are many ways we can also get optimal lambda by using our library. So once you read ovariant data and actually specified generated event data with the value of 1, then from FlexServe library, you can use FlexServe function and specify independent variable as 1 and specify distribution as exp. Then actually you can get lambda. So if you take exponential of coefficients, then actually this is optimal lambda, right? This is same as Excel output. And the second way is to use a library, and if you use serve function and same as approach, so specify independent variable as 1, then you can get actually coefficients. So if you take exponential of negative coefficients, then you can get this lambda, right? Again, so FlexServe, you can directly calculate lambda from exponential formula, but in survival analysis, you need to consider negative sign. And the third method is to use EHA library. So if you use AFT-REG, accelerated failure time regression, and specify distribution as Weibull and shape as 1, then it actually assumes exponential distribution. So again, exponential of negative coefficients, then it also shows you optimal lambda. All right? So I hope previous video and this video was useful to understand how to get optimal lambda in XLNR. And the purpose of introducing this method is to link with survivor analysis. In survivor analysis, as you can see, lambda actually is equal to psi of Zi covariates. There's one good reference site I have used for this video, and as you can see, the hazard rate would be the same for any two individuals with the same covariate values. Although there are many possible choices for psi, one simple and natural choice is like this. So psi of Zi is equal to exponential of regression form. So again, in survivor analysis, typically we have event data and sensor data. So the log likelihood should consider those two, right? Then finally, you can get this log likelihood, right? Again, lambda is equal to psi of Z, right? And we want to use this log lambda to get, to estimate beta, right? So I will show you how to use this log lambda in the next video. I will show you how to get how to get these estimates in XLNR. I hope it was useful to understand lambda of exponential distribution and how to get it in XLNR. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sang Kim. In the previous video, I tried to explain how to get the optimal lambda of exponential distribution. Based on this knowledge about exponential distribution, I would like to explain how to do exponential survival analysis in this video. I have found 3 ways to do exponential survival analysis in R. The first way is to use a survivor library. So if you use serve reg function and specify distribution as exponential, then you can get this output. And it focuses on survival rate. That's why age has a negative sign of coefficients. Typically, in survival analysis, when aging, the coefficients actually takes a negative sign, right? And we specify distribution as exponential. That's why scale fixed at 1. And log likelihood is minus 91.2. Right. And there are other ways we can do survival analysis. The second way is to use EHA library. So in EHA library, you can use AFT-REG function, which means accelerated failure time regression, and distribution as Weibull with shape 1. Then it means exponential distribution. Then you can have these coefficients. As you can see, these coefficients, sign of these coefficients is opposite of survival analysis because it focuses on failure rate, right? So when aging, failure rate increasing. And this is low likelihood. And the last one is to use FlexServe library. And if you use FlexServe reg function with exponential distribution, you can have this output. As you can see, it provides rates and Rx and age. Actually, in survival analysis, the intercept term is around 12, but it shows different value. However, if you take logarithm of rates coefficients, then you can have same output, right? Right. So in in this slide, I want to explain how to get these coefficients in Excel. Right. So let me remind you of how to get regression coefficients for Cox proportional hazard analysis first. So let's set initial value as 0. Then x beta can be calculated by a merge of independent variables, comma, and coefficients, and press Ctrl Shift Enter. Right? We can apply this formula for other cells. Again, click Ctrl Shift Enter. Then exponential of x beta can be calculated by exp function. And log likelihood for each observation can be calculated by if fu stat equals 1, means there's an event, then we can calculate x beta minus log of sum of exponential x beta and fix the last cell, close, and if b1 is not equal to 1, let's set value as 0. Okay. Right, then sum of log likelihood we calculate by the sum function. Then we want to maximize this one, so click solver and set objective this one, and by changing value cells from these green cells and uncheck this box and click solve. Right, this is coefficients for Cox proportional hazard. Then let's move on. Let's calculate, let's get exponential regression coefficients in Excel, right? In the previous video, I explained how to, what lambda means, right? Constant hazard rate. Then we can calculate in exponential survival analysis. We can think of lambda as exponential of regression form. So x beta can be calculated by intercept term plus Rx coefficients times Rx plus age coefficients times age independent variable. Then lambda can be calculated by exp function. Then log likelihood can be calculated by delta, it's an event, so fu stat times beta z beta, so this one, and minus xi is actually fu time times exponential of z beta means lambda. All right. So we want to maximize this low likelihood. Then click solver. And we want to maximize set objective, this one, and by changing variable cells. Okay, this one. And uncheck this box and click solve. Right, so same as almost same as our output, right? Small difference comes from, I think, different algorithm. So again, intercept term in Excel, it shows negative 12.12, but in R, the value of rates is this one. So actually, if we take log of 0.0000543557. Okay, this is almost same as Excel output, right? Right, so I hope it was useful to understand how to get exponential regression coefficients in Excel. In summary, uh, in our program, we may think of three different ways for exponential survival analysis. So if you use survivor library, it will focus on survival rate, right? And if you use EH library, FlexServe library, AFD-Reg or FlexServe-Reg, it provides actually regression coefficients and it focuses on failure rate, right? However, it has same output, interpretation. I hope it was useful to understand how to do exponential survival analysis in XLNR. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube videos. I'm Sang Kim. In this video, I'm going to show you how to calculate the standard errors of exponential survival analysis. In the previous video, I showed you how to do exponential survival analysis in R by using subreg function or AFD-reg function or flexor-reg function. And also I showed you how to estimate these coefficients based on this log likelihood function, right? There's one reference book for this video. Hosmer, Ramshaw, May actually published a very good book to understand survival analysis. And according to this book, log likelihood function can be calculated by sum of event times log of PDF plus 1 minus event times log of survival function. And it can be simplified like this form. And as you know, in order to calculate the standard error, we need to calculate second partial derivative of the log likelihood function. And it can be defined like this format. So in this video, let me show you how to get these standard errors in Excel. Again, let me use this simplified log likelihood function formula. And let's use this second partial derivative form to calculate standard error. Yt is equal to log of FU time and Z, this one, Yt minus, sorry, let's set initial value for B0, B1, B2, log of average of FU time around 6, so let's say 6 and 0 for initial as an initial value. Then Z can be calculated by Yt minus B0 minus B1 times Rx minus B2 coefficients times age. Then log likelihood, this formula, event times G minus exponential of Z value. So we want to maximize the sum of this log likelihood. Okay, let's use solver. This one. Set objective, sum of log likelihood. We want to change value from these cells. One click, uncheck this box, and click solve. Right. Then let's click again solver till it's not changing, because I think Excel solver is a little bit sensitive about this optimization. Okay, it's changing. Let's click solver again. Okay, it doesn't change anymore. So as you can see, this is very similar to this our output, right? So we can use this formula to calculate to get estimated coefficients, this one. And let's move on how to calculate standard errors. So this part can be calculated by matrix form. So if row, let's fix row and column. So if row and column is same, then let's get exponential of z value. If not, let's give value as 0. Control C and Control V. Okay. I actually used a conditional format to check whether only diagonal elements are over value 1, right? Then again this formula. Let's get information matrix. So emerge transpose of independent variable, including intercept term. I mean this one. Then exponential of zi and emerge times independent variables and press Ctrl Shift Enter, right? Then we need to calculate the inverse of this matrix because this is information matrix, and inverse of information matrix, press Ctrl Shift Enter. Okay, then standard error for V0 can be calculated by square root of first diagonal element and square root of second diagonal element and square root of third diagonal element. Then it is the same as R output, right? Then Z can be calculated by coefficient over standard error. Okay, and then p-value is actually 2 times 1 minus normal distribution of z value, comma, mean as 0 and standard deviation as 1. Not true because cumulative. Sorry, we need to add one more parenthesis. And Ctrl C. So let's use absolute value of ABS of z value. Then Ctrl C and Ctrl V. Then it's same as our output. So as you can see, under 5% significance level, age variable is significant. However, Rx variable is not significant under 5% significance level. So again, this book, Hosmer Ramsher May, actually provided very good background of log likelihood and standard error for exponential survival analysis in parametric survival analysis chapter. I hope this video was useful to understand how to calculate standard errors for exponential survival analysis. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube content. I'm Sang Kim. Today I would like to help you understand about Weibull distribution, which is one of the popular distributions for parametric survival analysis. The characteristics of Weibull distribution can be explained by this sentence. If the quantity x is a time to failure, the Weibull distribution gives a distribution for which the failure rate is proportional to the power of time. This is cumulative density function for survival for Weibull distribution. As you can see, there are 3 parameters: beta, eta, and gamma. We typically set gamma as 0 because we can standardize time variable. So the most important parameters are beta and eta. Beta is actually a shape parameter and eta is scale parameter. In Wikipedia, as you can see, it used different Greek letter, K and lambda. this one. And Excel function provides wife.dist function. So you need to specify time and shape and scale and true for CDF. This is a probability density function for wife distribution. And again, veta is a shape parameter and eta is a scale parameter, right? Again, we can set gamma as 0. And this is the formula in Wikipedia. And in Excel, we can use wife.dist function. So time, variable, and shape and scale parameter, and first option. Right, let's simulate some results while changing scale parameter with fixed shape parameter. So as you can see, if after fixing a scale as 8, and if you change a shape from 1 to 16, as you can see in scale 8, time as 8 value, then it shows highest probability. And the orange curve shows highest peak because the shape parameter takes value as 16. So we can draw this graph in R. So this is the R program to draw this graph. I will share anyway this R program in YouTube. And we can also draw same graph in Excel. So this is main Excel formula for this one. So we can draw this graph. Right, this is PDF. While changing scale parameter with fixed shape, then we can see this PDF. As you can see, if you change the scale from 3 to 10, then as you can see, it moves from left to right. Okay, but the highest probability goes down. So we also can draw this graph in R and Excel. In our program, actually, as you can see, we can use the wife function. Then you can draw this graph in R. And in Excel, you can draw same graph. And this is a main Excel formula. Okay, you can draw this graph. Right, reliability function. Actually, the concept of reliability function is important, and also it is same as survival function, ST. So RT, capital RT, can be calculated by 1 minus capital FT, cumulative wife distribution. And in ST is actually same as RT, and if you consider derivative of capital FT, then a small ft, PDF, can be calculated by negative st, the derivative form of about x. So reliability, as I mentioned, same is survivor function. So as you can see, if you fix scale as 8 and change shape from 0.1 to 3, then the graph shows like this, right? So this is when shape value as 3, then it shows opposite of S curve. So if you changed shape as like 4, then or 5, then as you can see, steeper S curve we can see. And again, if you fix shape but change scale from 5 to 10 or 12, then as you can see, the opposite S curve actually moves from left to right. So this is kind of characteristic when you change shape and scale about reliability. There are good two reference sites I found. So I recommend you to visit this website or read this book. So the main background of this video is to help you understand about waiver distribution, because I'm going to upload more videos about waiver survivor analysis. So I hope it was useful to understand waiver distribution for parametric survivor analysis. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sangwoo Kim. Today I'm going to explain how to estimate parameters for waiver distribution by maximum likelihood method. Let me use ovariant data, and the data has been sorted by FU time. In this video, I'm only going to consider FU time variable, and it means I will assume that event for every FU time has been occurred. I have found 4 ways to estimate parameters for waiver distribution. The first way is to use waiver tools, so you can convert data by using reliability underscore data function. Then you can use ml underscore estimation function. Then you can get estimated parameters. It shows actually mu and sigma or eta and beta. Alright. In survivor library, you also can get intercept and scale by using servreg function while specifying this as waiver. Then it provides intercept and scale. The intercept is same as mu, and scale is same as sigma. And also again, waiver tools provides eta and beta. In FlexServe and EHA library, you also can estimate parameters for waiver distribution. So in FlexServe, you can use FlexServe function. Then you can get shape and scale. This shape value, estimated value, is same as if you convert shape as exponential of negative this value, is same as sigma, and scale is same as mu. And in EHA, as you can see, the expression is different. The name of parameter is different. As you can see, it use log scale and row shape. So row scale is same as scale, and row shape is same as shape in FlexServe library. Right, let me show you how to estimate parameters for waiver distribution in Excel. So typically I used log likelihood formula to estimate parameters by maximum likelihood. But in this video, let's try to use a built-in function, which is waiver.dist function, to estimate parameters by maximum likelihood method. So let's say initial value is 0 over 0, then PDF dist and time variable, comma, and alpha, comma, theta, comma, and false. Alright, so again, alpha and beta, when we think of PDF or waiver distribution, we can think of changing initial value. So personally, I use initial beta value from average of FU time. Roughly is around, let's say, 600. Okay, and alpha should be greater than 0. So let's say initial value as 1. Then PDF, we can use this formula for other cells, right? And the log likelihood for each observation can be calculated by log of B2 Okay, and sum of log likelihood. So we want to maximize this sum of likelihood while changing alpha and beta in Excel. So click solver, okay, and set objective from F5 and changing variable cells from F2 and F3. Then uncheck this box and click solve. Okay. Actually, I have simulated, I have tried to estimate alpha and beta before taking this video. Then I noticed that actually solver provides different result once you click again. Okay, I don't know why, but I recommend you to run solver more than 2 times anyway in Excel. It's not changing anymore. Right. So we were able to get estimated parameters alpha and beta. So 1.85, same as beta, and 674, this one eta, right? So in R, actually it says beta and eta, but in R, actually it's alpha and beta, right? Alpha is known as shape, and beta is known as scale in Excel. So sigma can be calculated by 1 over alpha, and mu can be calculated by log of beta, right? So this one is same as mu and sigma. And I have also noticed that different R libraries actually use different name of estimate parameters. In Wyver tools, as I showed you, we can calculate beta and eta, and we can convert it to sigma and mu by using this formula. In Survivor library, actually you use scale and intercept, and scale. So this value is a scale in Survivor, and 6.5 is actually intercept value. And FlexServe and EHA, it provides actually these two values. And in FlexServe, the name of estimate parameter is scale and shape, and EHA use log scale and log shape, right? So log shape, this one, and shape, this value in FlexServe, can be converted to this value by using exponential of negative shape value in FlexServe. Then it's same as scale value in Survivor library. So this is how to estimate parameters for Wyver distribution by using Excel. I hope it was useful to understand how to estimate parameters for Survivor Wyver analysis by maximum likelihood method. Right? Typically, I think it's easy to use R function. Then you can estimate parameters by using Wyver tools or Survivor or FlexServe or EHA library. Right? I hope it was useful to understand how to estimate parameters in R and Excel. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sam Kim. In this video, I'm going to show you how to estimate parameters for Wyver Survivor analysis by maximum likelihood method in Excel and R. Let me use sorted ovarian data for this video. FEO time is time variable, and FEO stat measures censoring status. So 1 indicates event and 0 means it is censored. Right. There are some R programs for Wyver analysis. So I have found 4 ways. So from Wyver tools, if you convert data to reliability data, then you can use ML estimate function. Again, you can get mu and sigma, and also eta and beta, right? The second way is to use a reg function. Then you can get intercept and scale, right? So as you can see, intercepts is actually means mu, and scale is same as sigma. The third way is to use flexserve library, and if you use flexserve function, then you can get shape and scale, right? And in EHA library, there are 2 ways you can use AFT-reg, accelerated failure time regression function, and YVREG function. There could be some difference, but mostly AFT-reg and YVREG provide similar output. So log scale means scale in flexserve, and log shape is almost same, and this is also similar to shape. Okay, as you can see, so there's a relationship between mu and eta and sigma and beta. So if you take let's say log of eta, then you can get view, right? Estimated view. And from beta, you can get, if you consider 1 over beta, right? You can have sigma. Okay. And if you take exponential of negative 0.1026105, then also you can have this value the same as sigma. I hope it was useful to understand the relationship between mu and sigma and eta and beta, right? And from flexserve and EHA library, you can have shape value, then you can convert it to sigma. Right. In Excel, I would like to show you 2 ways to estimate parameters for Wyver survival analysis. The first way is to use this log likelihood formula. There's one reference site I have used for this video, right? And one thing you need to be careful is about sigma and mu. Sigma is equal to 1 over alpha, and mu is equal to negative log of lambda. So let's calculate this part first. And this column D means this part. So column C, if you step times log of if you time, and t to the power of alpha t over, and let's use sigma and mu, this one. So 1 over sigma. So let's say sigma at value as 1. Okay. In terms of view, in Excel, you need to be careful about setting initial mu value. So let's get average of time. Then log of time is around 6.39. So let's say initial value for mu as 6. Okay, and t is sum of delta I, this one, this one, column B. Okay, then the last thing you need to do is to calculate log likelihood by using this formula. So D times log of alpha equals 1 over sigma, and plus d times 1 over sigma times log of lambda, so exponential of negative mu and plus 1 over sigma minus 1 and times sum of column C and minus lambda is exponential of minus mu and to the power of alpha 1 over sigma and times sum of the last term okay. Then we can use solver. So we wanna maximize sum of log likelihood by changing mu and sigma, and uncheck this box and click solve. Alright, as you can see, if we use log likelihood, this formula, then we can get mu and sigma. Okay. Alright, there is another reference site I have used for this video. So as you can see, the corresponding log likelihood can be defined by this formula. So we can think of Weiber probability distribution and survivor function, right? So this part, log of ft Weiber dot dist. Sorry, let's set shape. Let's initialize value for shape and scale as 1 and scale this part. So again, in Excel, it's important to set a right initial value. So the average of this value is around 600. So let's say 600. Okay. The log of Weiber dot dist and time variable, comma, and alpha, comma, and beta, comma, first, because it is PDF, and log of survival function. Survival function is actually reliability function, so same as 1 minus Weibull dist and time variable, comma, shape, comma, scale, comma, true, because it is CDF. Then if we consider these parts, we can convert it in Excel formula. If event has happened, then we can use log of ft. If not, let's get log of st. Then we want to maximize this log likelihood, sum of log likelihood. Okay. Then click solver again, changing variable value here. Okay, then click solve. Alright, as you can see, we were able to get alpha and beta, means shape and scale, this part. So in R, actually it provides mu and sigma. Again, let me show you how to convert it. So mu is log of scale, and sigma is actually 1 over shape. All right. Right, in this video, again in summary, I showed you how to estimate parameters by maximum likelihood method in R by using Wyver tools or Survivor or FlexServe or EHA library. In Excel, there are two ways you can use this log likelihood formula. Then you can estimate mu and sigma. If you use PDF and CDF for survival function, then you can estimate shape and scale, and of course you can convert it to sigma and mu. Right. I hope it was useful to understand how to estimate parameters for parametric survival analysis based on Wyver distribution in Excel and R. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sangwoo Kim. In this video, I would like to help you understand how to estimate parameters for Wyver survival analysis with covariates based on maximum likelihood method. Let me use ovarian data. There are two covariates, which are Rx and age. Let me show you how to do it in R first. So you can use survivor library. So if you use solve_reg function, you need to specify distribution as Wyver. Then you can get these outputs. You also can use EH library. So if you use Wyver function, then you can get these outputs. The main difference between two is actually the sign of coefficients. So this is how to interpret the result. In survivor library, if variable shows positive sign of coefficients, then actually Rx has got value 1 and 2. So when value 2 actually has higher survival rate compared to value 1. And for age, it shows negative sign. So when getting age, the survival rates is decreasing when getting age, right? So this is vice versa. So this is focuses on hazard rate. So when getting age, the hazard rate is actually increasing. And if you use this transformation, then you can get same outputs like in survivor solve_reg function. There is another function, FlexServe reg function in FlexServe library. Then you can get these estimated coefficients. Then let's also compare EHA outputs, right? Then if you use this transformation, then you can get same outputs. Right, let me show you how to do it in Excel. Secondly, so there is one good reference site I have used for this video. So the first thing is to transform time variable by using log transformation. Then you can use this log likelihood function. There are two parts, green parts and purple parts. So green parts are related to this part are related to events observation, and the purple part is related to sensor data. So let's get x value. So log of time variable. Then let's set initial value from B0 to sigma. So this is the average log of average of FU time. I typically use this value as initial value because in Excel, actually Excel is very a little bit sensitive about initial value when you use solver. So let's use 6 and 0, 0 and sigma as 1, because sigma cannot have 0 value. So G can be calculated by x minus b0 times b0 minus b1 times rx minus b2 times h over sigma. Right, then log likelihood. So we need to think of event case and sensor case. So if FU_stat equals 1, then let's use g minus exp of z minus log of sigma. If not, minus exponential of z. Okay, then we want to maximize sum of log likelihood. Click solver and set objective J7 cell and changing variable value, this one. Uncheck this box and click solve. Let's try to click again, solver. Let's see whether it's changed or not. Or be changed. Okay, let's try again. Okay, so this is final estimated value in Excel. As you can see, it's almost same as our output. And the main difference is this part, sigma. So we, in order to get this one, log scale, so log of sigma, right, we can have same output. So these are estimated coefficients for Wyver survival analysis in Excel. I hope this video was useful to understand how to do it, how to do survival analysis in R, and also how to estimate coefficients for survival analysis, Wyver survival analysis in Excel. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sangwoo Kim. In the previous video, I showed you how to estimate parameters for Wyver survival analysis with covariates in Excel and R. In this video, I would like to show you how to get standard errors of Wyver survival analysis with covariates in Excel, which is same as R output. Right, so let me quickly show you how to estimate coefficients based on this log likelihood function. So x variable is actually log of every time, right? Then let's set initial value for b0, b1, b2. So b0, again, I normally use average of log of every time, okay, around 6.39, so let's say 6, and then b1 0 as an initial value, and b2 also 0 as an initial value, and sigma 0.1, because sigma cannot be 0, right? Then z variable can be calculated by log of FU time minus b0 minus b1 coefficients times rx minus b2 times h and over sigma. Right, then log likelihood can be calculated by if FU_stat equals 1, then we can use this gray part. So z minus exponential of z and minus log of sigma. If not, we can use negative exponential of z value. Alright. Then sum of log likelihoods. So we want to maximize this sum of log likelihood while changing these coefficients. So click data and go to server. Okay, and set objective from sum of log likelihood. We want to maximize it by changing variable cells. This one. And uncheck this box and click serve. Okay, again, as I mentioned in the previous video, we need to click more until it doesn't change anymore. Okay, and click again. Okay, okay, it doesn't change anymore. Right, so this coefficient is almost same as our output. Again, the small difference comes from different algorithm. Log scale is log of sigma. Right, this is how we can estimate coefficients by using Excel, right? So let me show you how to get these standard errors and z and p-value in Excel. So there's one reference book I have used for this book. There is a matrix information matrix formula to calculate standard error, right? But actually there is 1 over sigma hat squared, so we need to be careful when we use this one when you calculate matrix computation, right? So let's copy z value, and again, as you can see, V matrix consists of diagonal of e to the power of zi. So exponential z. Then we need to make a V matrix by using exponential of z. So if equals this one, then let's get exponential z value, fixed column. If not, let's give a value as 0, and Control C and Control V, right? So I use conditional format to highlight diagonal elements, this one, and let's give a name in Excel. Let's say as a V. And then also let's give a name for X matrix. So I added one more column here to make it design matrix. So let's give a name as X. And for column Z, let's give a name as Z. Alright. Then let's get information matrix by using this formula. The first part is X prime times V hat times X. So emerge transpose of X comma V, and again emerge comma X and over sigma squared, this one, so sigma squared, and press Ctrl Shift Enter. Right, and this one X prime times V hat times Z hat. So emerge transpose of X comma V, emerge comma Z, and divide by actually sigma, not sigma squared, this one, and then press Ctrl Shift Enter. Okay, and this value is same as this one, and just transpose values. The last part, this one, M is actually sum of events, and we don't need to you don't need to multiply by 1 over sigma squared. This is one thing we need to be careful. Anyway, let's get merge transpose Z comma V, and again merge comma Z, okay, and plus sum of events, and press Ctrl Shift Enter. Right. Then we need to calculate inverse of information matrix and inverse of information matrix. Press Ctrl Shift Enter. Okay. And the diagonal elements is actually a standard error for each coefficient. So standard error for B0 can be calculated by square roots of first element and square root of second diagonal elements, and for V2 square root of third element and square root of first elements. Okay, then Z value can be calculated by coefficients divided by standard error. And again, this one, we need to, in R, actually use log scale. So let's change it, log scale of standard error. Okay, so this is same as R output, and P value can be calculated by two-sided test. So 2 times 1 over normal distribution of value, comma mean as 0 and standard deviation as 1, and then true cumulative to specify cumulative distribution. Okay, and let's use absolute value of Z. Okay, then Ctrl C and Ctrl V. Okay. Okay, as you can see, this is same as our output, right? The small difference actually comes from small different coefficient values. Again, this is because of different optimization algorithm, I think. But as you can see, we were able to get p-value. Then again, under 5% significance level, we can say that V2 and sigma is significant, right? So the main purpose of this video is to calculate standard error by using information matrix. This information matrix is come from actually second derivative form of log likelihood. I hope it was useful to understand how to calculate standard error by using information matrix. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sang Kim. In this video, I would like to show you how to estimate parameters for wave distribution by using wave plot in Excel and R. In our program, you can use wave.wp function from wavelist library. So I have used FU time data, then it provides estimated shape and scale. So let's draw a PDF plot by using theoretical value rather than actual FU time for better graph. Then PDF can be calculated by wave.dist function and alpha from shape and beta from scale value. And first, because it is I want to draw a PDF plot. Okay, let's change X label, X-axis label. Right, this is a theoretical PDF plot when you use FU time data. So let me show you how to get this estimate shape and scale in Excel. Right, FU time data has been sorted out from a small number to a large number, and the rank is actually from 1 to the last one, 26, and probability points. There's one reference site I have used for this video, and there are 4 formulas for rank-based normalization procedure. So I have tried 4 of them, 4 ways, and then I think our program used this ranked formula. So probability points can be calculated by rank minus 1 over 2 divided by count of FU time. Reliability can be calculated by 1 minus probability points, and log t can be calculated by log of FU time, and y value can be calculated by log of minus log of reliability. Then we can draw scatter plot. Okay, so we want to actually, if it this dotted points follows actually has linearity, then I think it's right distribution for right y-word distribution. So from this graph we want to calculate intercept and slope, and then we can calculate shape and scale. So intercepts can be calculated by intercept function in Excel. Y value from column F, and comma X value from log T. Then slope can be calculated by slope of y, comma, and log T. Right. Then shape, estimate shape value is same as slope, this one, and scale can be calculated by exponential of negative intercept over slope. Right. So this is same as our output, and shape is also same. Right. So in this video, again, I wanted to show you how to get estimated shape and scale based on y-plot function. Right. So in R you can use y.wp function, and in Excel you can use this approach. Then you can get shape and scale. I hope it was useful to understand how to use y-plot to estimate parameters for y distribution. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sang Kim. In this video, I would like to show you how to do rank regression for parametric y distribution in Excel and R. The rank regression method for parameter estimation is known as the least square method. This is a more formalized method of the manual probability plotting technique, in that it provides a mathematical method for fitting a line to plotted failure data points. There are 2 reference sites I have used for this video. In our program, you can use rank_regression function in YTools library. Then this function fits an X on Y regression to linearize toward 3 parameter lifetime distribution. Please remember that in our program we can use Lm function for typical linear regression. Then Lm function fits y on x regression, right? Rank underscore regression fits x on y. Then beta 1 hat can be calculated by covariance of y and x divided by variance of y, and intercept can be calculated by x bar minus beta hat times y bar. There is another reference site I have used for this video, and this is typical rank regression function formula. Then yk can be calculated by using this formula, and xk can be calculated by log of time, and fk are probabilities, so they cannot be directly observed. Better choice for fk is a median rank, and fk can be calculated by using this formula. In our program, again, once you extract data for analysis, then you can use rank underscore regression function and specify distribution as y-bar. Then you can get estimated parameters for mu and sigma or eta and beta. Let me show you how to get this one in Excel. So rank can be calculated by 1, 2, this one. The data has been sorted from smallest to largest time. Then median rank can be calculated by rank minus 0.3 over count of our data plus 0.4. Then y can be calculated by log of 1 over 1 minus 1 over 1 minus median rank, and x can be calculated by log of time. Firstly, let's regress y on x to compare with x on y. So variance of y and x divided by variance of x. Then mu can be calculated by average of x minus beta hat times average of y. Right, so we are more interested in this one to get same output in R. So sigma can be calculated by covariance of y and x divided by variance of y. Then mu can be calculated by average of x minus sigma hat times average of y. Right, so this is same as our output, and beta can be calculated by 1 over sigma, and eta can be calculated by exponential of mu. This is same as our output, right? So I hope it was useful to understand how to do rank regression in Excel and R. Please click like and subscribe if it was useful for you, and thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sangwoo Kim. In this video, I would like to show you how to calculate the Cox-Snell residuals in Excel and R. The Applied Survivor Analysis book, written by Hosmer, Ramshaw, and May, provides this information, this expression. The residual is called the Cox-Snell or modified Cox-Snell residual. This terminology is due to the work of Cox and Snell, who showed that the values of H hat
maybe thought of an observations from a sensor sample with an exponential distribution and parameter equal to 1. So once you get Cox-Net residuals, you can test whether the residual follows exponential distribution with a parameter equal to 1. But typically we use this Cox-Net residual as a graphical analysis. In our program, it actually provides residuals related to martingale, deviance, score, Schoenfeld, or scalar Schoenfeld, etc., related to Cox proportional hazard analysis. So it doesn't provide Cox-Net residual. Anyway, let's try to understand Cox-Net residual in this video. Right, there's more reference sites I have used for this video. The Cox-Net residual for case J in a survival model can be written by this form. This is actually also can be written by this form. And that means the product of an estimated baseline hazard, HLT, and the hazard ratio for the case calculated from the vector beta hat of regression coefficients. Right? And the Cox-Net residual can be written by this form also. Yeah. All right. So there's another websites I have used to understand Cox residuals. The diagnostics based on Cox-Net residuals are based on fitting a Kaplan-Meier or Nelson-Aron curve to residual for each observation and comparing it to that of standard exponential. In terms of shortcoming, one drawback to the Cox-Net residuals is that they don't provide much insight into why the model's assumptions are violated. In our program, actually, you can install LDA tools from DevTools. Then you can use gg_snell function, Cox-Net function. Then you can draw this graph. X-axis are actually Cox-Net residual, and Y-axis is cumulative hazard. And also, you can get Cox-Net residuals and cumulative hazard and survival rate. Right, let me show you how to get Cox-Net residuals in Excel. Let's use this CPH1 output. There are two covariates, Rx and H. Then you can set up initial value as 0. Then X veta can be calculated by Rx times Rx coefficient plus H times H coefficient. Right, then exponential of X vector can be calculated by using exp function. Then partial log likelihood for each observation can be calculated by if F(stat) equals 1, then X veta minus log of sum of exponential X veta as a counting process. Let's fix the last cell. And if not, F(stat) is not equal to 1, then let's give a value as 0. Right, then we want to maximize sum of partial log likelihood. Let's use solver. Okay, this form. So set objective as sum of log likelihood and changing variable cells from covariates, and uncheck this box and click solve. Right, this is estimated coefficients for Rx and H. Baseline hazard if F(stat) equals 1, then 1 over sum of exponential X veta, and let's fix the last cell. If not, let's give a value as 0. Then let's get cumulative baseline hazard. The first row is same as baseline hazard, and from second row, baseline hazard can be calculated by baseline hazard for second row plus previous one. Okay, then Cox-Net residuals can be calculated by cumulative baseline hazard times exponential of X veta. Okay, this is Cox-Net residuals, but in our program, as you can see, it has been ordered from smallest to largest. So let's copy data here and paste it here. And then let's change order from smallest to largest. Then this is, as you can see, this is same as our output, right? Then let's get cumulative hazard and survival rate, CDF and F. Actually, I want to also show you how to draw this graph in Excel. So we need to calculate coccinelle residual and cumulative hazard anyway. So number of observations at risk can be calculated from count of any column from here. Then let's fix the last cell. Okay. Then hazard can be calculated by FU stat over number of observation. Okay. Then cumulative hazard can be calculated by from this formula, second row hazard from second row plus previous cumulative hazard. Then this is same as this our output. Then survival rate can be calculated by exponential of minus cumulative hazard. This is same as our output. Okay, and CDF is actually 1 minus survival rate. Then F can be calculated by exponential of minus Cox-Snell, and then 1 minus. Okay, this is MS output. Actually, I considered I used this one. Coxinel residual is same as negative log of 1 minus f, right? So f can be calculated by exponential of negative Coxinel. Okay, so let me draw this one. I need Coxinel residual here and cumulative hazard, this one. Let's give an ID like this. Actually, we need a little bit more Excel trick because of this step expression. So as you can see, this there's at this point there's no actual data, but we need to generate this artificial data to make it as a step. So let's think about this point. So this point has same x value, this one, and right, same y value, but actually also x value is from this one. So let's get 0.0001, and x this one, the x value from this one, and y value from this one. So if we generate more columns, more data, okay, we don't need this one. Okay. And copy and paste. Let's change the order from by using ID. Right. Then let's draw graph by using this Coxinel cumulative hazard, and click insert, go to scatter, and choose this one. Okay. Let's change axis. Okay. Then let's draw this red line because the slope is actually 1 because exponential distribution with parameter as 1. So like this. Right. So the x-axis is actually Coxeter residual and y-axis is cumulative hazard. Right. I think it looks like very similar to our output. Anyway, the main purpose of this video is to help you understand how to calculate Coxeter residuals in XLNR. This one. So I hope it was useful to understand how to calculate Coxeter residuals in XLNR. Please click like and subscribe if it was useful for you. Thank you.
Hi everyone, thanks for watching my YouTube contents. I'm Sang Kim. In this video, I would like to help you understand how to calculate martingale and deviance residuals in XLNR. There are a couple of websites I have used for this video, and there are 3 types of diagnostics for the Cox model. The first one is testing the proportional hazard assumption. Second one is examining influential observations or outliers. The third one is detecting non-linearity in relationship between the log hazard and the covariates. So Schoenfeld residuals, martingale residuals, deviance residuals are popular to analyze residuals. So in this video, I would like to focus on martingale residual and deviance residual. Martingale residual is to assess non-linearity, and deviance residual is to examine inflation observations. According to Hosmer, Ramshaw, and Maybu, Coxeter residuals can be calculated by using this formula. The first part is, as you can see, it is baseline cumulative hazard. And the second part is covariate part. So these are called Coxeter residuals. Actually, martingale residuals is event minus Coxeter residuals. So the meaning of this martingale residuals is the discrepancy between the observed value of subject failure indicator and its expected value. Martingale residuals are very useful to identify outliers and choose a functional form for the covariate. However, it has a drawback. But the sum of squares of martingale residuals cannot be used as a good measure of goodness of fit. The deviance residual is an alternative that does have this property. I mean, a measure of goodness of fit. This is deviance formula, and these residuals are symmetrically distributed with expected value 0. In our program, once you have Cox proportional hazard model, then you can use residual functions and specify type as martingale or deviance. Then you can get these martingale or deviance residuals. Right, let me show you how to get these Coxeter, martingale, deviance residuals in Excel. Let's say initial value. Let's set initial value for Rx and H as 0. Then you can calculate x vita. X vita can be calculated by Rx times Rx coefficient plus H times H coefficient. And exponential of x vita can be calculated by using exp function. And partial log likelihood can be calculated by if fu stat equals 1, then x vita minus log of sum of x vita as a counting process. If not, let's set value as 0. We want to maximize this partial log likelihood. Right, then go to data tab and click server. So we want to maximize this cell by changing coefficient values here.
then click solve. Right. These are estimated coefficients for Rx and age. So baseline hazard, if you use that, equals 1, then 1 over sum of x beta. If not, let's give a value as 0. Right. Then cumulative baseline hazard for first row is A, and the second row for cumulative baseline hazard can be calculated by this plus this one, previous one. Right. So Cox-Snell again. This one. Cumulative baseline hazard times exponential of x beta, this one. Then martingale residuals is actually event. If you use that, means minus Cox-Snell. These are same as our output. Right. Then deviance can be calculated by using this formula. So if sine of martingale residual is greater than 0, then let's give a value square root of minus 2 times martingale residual plus delta I is if we use that times log of if we use that minus martingale right. And if martingale residual is less than 0, and minus same formula. Okay, this is same as our output, right? So I showed you how to get martingale residual and deviance residual in Excel. So in summary, martingale residual is the observed value of subject failure indicator and its expected value. So martingale residual is 1 minus Cox-Snell, and deviance residual is to actually make martingale residual as symmetric to have symmetric distribution, right? I hope it was useful to understand how to calculate martingale residuals and deviance residuals in Excel and R. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sang Kim. In the previous video, I showed you how to calculate martingale and deviance residuals in Excel and R. In this video, I would like to show you how to use plots for martingale and deviance residuals for Cox proportional hazard analysis in R. Again, in summary, there are 3 types of diagnostics for the Cox model: testing the proportional hazard assumption, examining inflation observations or outliers, or detecting non-linearity in relationship between the log hazard and the covariates. Martingale residual is useful to assess non-linearity, and deviance residual, which is same as symmetric transformation of the martingale residuals. And this is also useful to examine influential observations. So let me focus on martingale residual plus to assess non-linearity in this video. So let me use our program. And let's activate survival library, and let's use ovarian sorted data, right? So ovarian sorted data looks like this, and FU time has been sorted from smallest to largest FU time. Right. Let's get we are interested in linearity. So let's get a null model from ovarian sorted data. So CPH0, Cox proportion hazard null model, and Cox pH, and serve FU time, and FU stat, and no covariate, data equals ovarian sorted. Okay. Then let's get residual from null model. Residuals CPH0 and type equals martingale. In the previous video, actually, I used Rx and age variable as covariate. So let's focus on Rx and age variable, right? So let's draw plots for Rx variable first. So x equals sorted Rx, y equals Res0. Then we can draw lines with. Then as you can see, there's slight linear, it shows very small linearity, right? Of course, you can consider, let's draw this graph again from CPH1 model, which includes Rx and age variable. So CPH1. Data equals ovarian sorted and Rx1. Martingale. Then so please remember this graph. This is from null model, and let's get same plots from CPH1 model. All right. Compared to previous plots, it shows almost no linearity, right? Once you include Rx variable in the model. To make it clear, let's use a continuous variable. So let's use this one. Okay. And instead of Rx, let's use age variable. Right, as you can see, it shows very strong linear relationship between age covariate and residual from null model, right? However, if you get the same graph from CPH1 model, it shows there's no linearity, right? Because once you include age variable, age actually explains lots of parts from Cox proportional hazard model, right? So again, in summary, without having any transformation, if it shows linearity, once you include it in the model, then you can directly use this covariate in the Cox proportional hazard model. So let's use PBC data. This is actually from survivor package. So PBC is the abbreviation of primary biliary, I think, and cirrhosis. Not sure whether the pronunciation is right. Anyway, so data let's see PVC data structure. Right, so we are interested in status and time, right? Then let's get another model and time and status 2 and no covariate. Then we can get plus x equals PVC biliary and y equals residuals from fit 0. There should be comma here. Confine function residue, sorry, there's typo, sorry. Right, it shows this pattern, and let's include lines here. Right, as you can see, a biliary variable without having any transformation has a relationship with residuals like this. It doesn't have. It's hard to say it has. It shows it has linearity, right? So we can think of transformation of biliary variable. So plot x equals PVC. Sorry, log of PVC and biliary. And y equals same residuals. And let's add lines with log transformation of biliary variable. Right. So once you actually consider log transformation, actually log of biliary variable shows linear relationship with residuals with null hypothesis. Then we can use like Cox proportional hazard model like this. Right. So again, sorry, we need to include log transformation like this. Right. This is how we can use martingale residuals to improve your Cox proportional hazard model in R. I hope it was useful to understand how to use martingale residuals for Cox proportional hazard model. Please click like and subscribe if it was useful for you. Thank you. Hi everyone, thanks for watching my YouTube contents. I'm Sang Kim. In this video, I would like to show you how to calculate Schoenfeld residuals or scaled Schoenfeld residuals for Cox proportional hazard analysis in Excel and R. The Cox proportional hazard model makes several assumptions, so it is important to assess whether the fitted Cox regression model adequately describes the data. The first one, testing the proportional hazard assumption, we can use Schoenfeld residual. So Schoenfeld residuals is to check the proportional hazard assumption. David Schoenfeld actually published an article in Biometrica in 1982, and the article name is Partial Residuals for the Proportional Hazard Regression Model. And these are main parts to understand partial residuals, which is same as Schoenfeld residual. And let's try to understand what it means. So as you can see, this is a crucial part to understand Schoenfeld residual. And you may have difficulty to understand this part. So expectation of xi given risk set of time I. It can be calculated by using this formula. So what does it mean?
So there's one reference site I've used for this video. The Schoenfeld residual vector is calculated on a per event time basis. At the jth event time, Tij of the I subject, the Schoenfeld residual can be calculated by this form. So this is the difference between the I subject covariate vector at time ij and the average of the covariate vector over the risk set at time ij, right? And there are another two reference sites to understand scaled Schoenfeld residuals. So as you can see, scaled Schoenfeld residuals can be calculated by using number of events times variance of beta times Schoenfeld residual. And in our program, actually, we need to add estimated coefficients to get scaled Schoenfeld residual. In our program, after you calculate, you get Cox proportion hazard model. Let's name it as CPH1. Then you can get Schoenfeld residual by using residual functions with Schoenfeld type specification. And also, scaled Schoenfeld residual can be calculated by using this command in R. As you can see, you need to calculate variance of beta hat in order to get scaled Schoenfeld residual. So in video 277, you can check how to calculate standard errors of coefficients for Cox pH analysis in Excel and R. So in this video, let me show you how to get these Schoenfeld and scaled Schoenfeld residuals in Excel. Let's first get coefficients. Right, so I initially set coefficient value as 0. Then x beta can be calculated by Rx times Rx coefficient plus age covariate times age coefficient. Then exponential of x beta can be calculated by using exp function. And partial log likelihood can be calculated by if stat equals 1, then x beta minus log of sum of x beta. And fix the last step. And if f stat is not equal to 1, then let's say 0. Okay. Alright, we want to maximize partial log likelihood. Sorry. Let's use solver. Okay. We want to maximize this cell by changing this value. Right. Then let's get Schoenfeld residual. So this is the formula. If f stat equals 1, then covariate Rx and minus numerator part sum product xi then exponential of this part. Fix the last cell and divide by sum of exponential of x beta. If f state is not equal to 1, let's give a value as 0. Okay, then to make it clear, instead of 0, let's make it as empty. Okay, then for age variable, same approach. Out age variable. Over sum of this part f column right. So this is same as our output. There's more difference in coefficient part because of different optimization algorithm. But anyway, then let's get scaled Schoenfeld. So let's get Schoenfeld register here. Copy and paste. All right. Then let's consider this formula. So and merge Schoenfeld residue, comma, variance of beta, then plus Control Shift Enter. Right. So we need to actually add, multiply by a number of events. There are 12 events. This one. Then again, press Control Shift Enter. Right. Then finally, let's add estimated coefficients, the same as our output. Right, this is the same as our output. So I showed you how to get Schoenfeld residue and scale Schoenfeld residue in Excel. In summary, again, this is main formula to calculate Schoenfeld residue. And expectation of xi given risk set of ti can be calculated by using this formula. And it means actually this part, right? Difference between I subject covariate vector at time ij and the average of covariate vector over the risk set at time ij. Then you can get this Schoenfeld residue and scaled Schoenfeld residue. I hope it was useful to understand how to calculate Schoenfeld residue and scaled Schoenfeld residue for Cox proportional hazard analysis. Please click like and subscribe if it was useful for you. Thank you.
Hi everyone, thanks for watching my YouTube contents. I'm Sang Kim. In this video, I would like to show you how to do proportional hazard assumption test for Cox-Page model and Kaplan-Meier transformation in order to use Cox.GFH function in R. In the previous video, I showed you how to get these three different types of residues in Excel and R. And in order to clearly understand Cox.GFH function, you need to understand Schoenfeld residues. And in my previous video, video number is 295, it helps you understand how to calculate Schoenfeld residues or scaled Schoenfeld residues in Excel and R. There's one reference site I have used for this video. The function Cox.gfh function provides a convenient solution to test the proportional hazard assumption for each covariate included in a Cox regression model fit. For each covariate, the function Cox.gfh correlates the corresponding set of scaled Schoenfeld residuals with time to test for independence between residuals and time. Additionally, it performs a global test for the model as a whole. Right. As you can see in our program, actually, Cox.gfh function provides three different types of transformation. The first one is actually rank. If you specify transformation as rank, then x value takes this number. This is actually row number, which takes FUStat as 1. Right? Then also it provides chi-square statistic and p-value. And if you specify transformation as identity, then x value takes actual time data, right? And also it provides chi-square statistic. And the last one is actually KEM transformation. So if you specify transform as KEM, then x value takes Kaplan-Meier transformation value. Then y value actually is same as for all transformation. And as you can see, this is scaled Schoenfeld residuals. Then it also provides chi-square statistic. As you can see, all p-values are greater than 5%. It means that we can accept null hypothesis. So it means that we can say that it satisfies proportional hazard assumption. Right, and also in our program, if you actually activate serve minor, then you can use ggcox-gfh function. Then it provides this graphical expression. Then as you can see, it provides global Schoenfeld test and also individual test. This p-value is the same as this one, right? Kaplan-Meier transformation. Then again, this p-value is greater than 5%, so it means that each covariate and global test actually satisfies proportional hazard assumption. As you can see, this line actually flat, so it means that there's no linear relationship. So it means that we can say that it satisfies proportional hazard assumption. Lastly, let me show you how to get this value from Kaplan-Meier transformation. So number of risk can be calculated by using count function and fix the last cell. Then probability can be calculated by 1 minus FUStat divided by number of risk then survivor rate. The first row is same, and the second row for survivor rate can be calculated by previous survivor rate times probability, this one. Okay, then Kaplan-Meier transformation. The first one is actually 0, and the second row for Kaplan-Meier transformation value can be calculated by 1 minus previous one, this one. Right, then this x value, if FUStat equals 1, then take KM transformation. If not, let's make it empty. Right, so this is same as our output, right? So this is actually this one is the final result from Kaplan-Meier transformation. So I hope it was useful to understand how to get Kaplan-Meier transformation, how to do Kaplan-Meier transformation. And the more important thing is to understand how to interpret Cox.GPH function output, right? Again, the p-value is greater than 5%, so it means that it satisfies null hypothesis. So we can say that it satisfies proportional hazard assumption. I hope it was useful to understand proportional hazard assumption test and Kaplan-Meier transformation in R. Please click like and subscribe if it was useful for you. Thank you.